Now we move from consensus foundations into application architecture. Cosmos SDK chains are built from modules protected by keepers, persisted in stores, and changed through messages. Once you understand that flow, you can design custom blockchain functionality that is reliable, maintainable, and easier to reason about. So far, you've connected the big picture: Cosmos zones and hubs, ABCI++ communication, and a running SDK chain. In this section, we look inside the application itself, at how modules, state, and business logic fit together. A Cosmos SDK chain has two cooperating layers. CometBFT handles peer networking, consensus, and block production. Through ABCI++, those consensus events become application calls, checking transactions, finalizing blocks, answering queries, and committing state. The SDK application routes those calls into modules. Bank owns balances, staking owns validator logic, Gov owns proposals, Auth owns accounts, and custom modules define the business rules that make your chain unique. In the Cosmos SDK, a module is more than a folder of code. It is a boundary around one business capability, such as accounts, governance, tokens, or liquidity. Inside that boundary, the module owns its messages, state, keeper logic, and queries. Other modules should not reach directly into that state. They interact through keepers or explicit interfaces. This separation keeps complexity contained, makes behavior easier to audit, and supports cleaner testing and upgrades. AppModuleBasic is the module's setup-facing interface. It handles what the application needs before runtime wiring exists: registering codecs and interfaces, exposing transaction and query CLI commands, and providing default Genesis plus validation. The main idea is that this layer describes how the module is understood and accessed, not how it mutates state. Because it usually has no keepers and no direct store access, it stays lightweight, reusable, and safe during early app construction. AppModule is where a module joins the running application. After keepers and dependencies are wired, it exposes runtime behavior, initializing Genesis state, exporting state for upgrades or migrations, registering message and query services, and participating in block execution. If a module needs begin block or end block logic, this is the integration point. It acts as the adapter between isolated module code and the blockchain lifecycle. Module wiring is the construction phase of a chain. Store keys define where state lives. Codecs define how data is encoded. Keepers expose the safe ways to read and write that state. Dependency injection connects these pieces through narrow interfaces, so modules stay testable and replaceable. The critical issue is authority. Every permission should be explicit, minimal, and auditable, because a small wiring mistake can become a security or upgrade problem. A module becomes useful when its capabilities are exposed through stable interfaces. Transaction CLI commands give operators a path to create and broadcast messages that change state. Query CLI commands, gRPC services, and REST gateways provide read-only access for apps, wallets, explorers, indexers, and automation. The key contract is protobuf. It defines exactly what clients can send and what servers return. Strong interface design makes a module easier to adopt, test, and integrate over time. A keeper is the approved doorway into a module's state. Message servers, query servers, hooks, and other modules should ask the keeper to read or change data instead of touching the store directly. That creates one place to enforce rules: supply limits, ownership, permissions, and valid state transitions. When those checks live in keeper methods, the module is easier to audit, easier to test, and safer to integrate. Application state is one organized database, split into module-owned sections. The multi-store is the root that holds those sections. A keeper does not reach into state randomly. It receives access through SDK context and uses its assigned store key to open the correct KV store. From there, it reads and writes key value data. This keeps auth, bank, staking, and custom state isolated, easier to reason about, and safer to upgrade. A module's KV store often holds many kinds of data, so prefixes act like namespaces inside one physical store. One prefix might identify parameters, another balances, and another positions or denom metadata. The design rule is simple but important. Keys must be deterministic, stable, and easy to scan. Use unambiguous byte prefixes and canonical address or ID encodings. A good layout makes queries fast now and makes future migrations safer because old keys can still be interpreted consistently. Keys are also the query API for your module state. The primary key stores the canonical object, such as denom to metadata. Secondary indexes create alternate lookup paths, such as owner plus denom or admin plus denom, so queries do not require full store scans. Composite keys matter because byte ordering controls iteration, pagination, and range queries. The critical rule is consistency. Whenever the canonical object changes, every duplicate index entry must change in the same transaction. Design indexes from query requirements, not convenience. Users don't call module logic directly. They express intent through msgq types, send tokens, create a denom, vote, or update parameters. One transaction can bundle several messages, and signatures prove which accounts authorize those actions. During processing, the chain authenticates signers, validates each message, routes it to the responsible module, and executes it through the msgq server. Good message design is explicit and minimal, with permissions and validation rules that are easy to reason about. A mist server method is the transaction's execution pipeline. For something like create denom, it first checks that the message is well-formed, then verifies that the signer has authority. Only then should it call the keeper to change state. After state changes, it emits structured events describing what happened and who was involved. Those events let explorers, indexers, relayers, and backends observe execution without re-implementing module logic. You now have the core Cosmos SDK mental model. Modules define boundaries. Keepers guard access and invariance. Stores shape durable state. Messages drive authenticated changes. Next, you'll apply this by building a simple custom module, then strengthen it with review, documentation, and testing practices.